Hey, arcade fans. No. Hey, video game nerds. Hey, arcade game nerds. One of those has got to be right. We're here to give you an update of what's going on with the Miss Pac-Man um, and uh, tell you what we're going to be doing next. Um, One of the things I said earlier about what makes the Pac-Man and the Miss Pac-Man and the Galaxian systems unique is that they had a single logic board. This is the Miss Pac-Man logic board. They had a single logic board where a lot of other arcades have separate boards for the audio drivers and the power filters and a whole bunch of other stuff. This board has everything on it. Right here we have these are the power systems that turn the AC into DC current for the two voltages for the 12 volts and the 7 volts. And that's why I couldn't just get a power switching power supply and swap it out, because this board wants AC. Now I could bypass it and hack it and get it to work with the switching power supply, but I'm really trying to keep this as close to normal as possible. And so the last episode I was trying to find one of these unique power transformers that they have in the Pac-Man system. That's a power transformer that has both a 12 volt CT and a 7 volt CT in a single transformer, and I couldn't find one. So I contacted a bunch of custom transformer companies and sent them a query, and I got the results of that. We'll talk about that. But at the very end of the episode, I said, hey, there's a Pac-Man power supply on eBay, so let me just order this and we'll ship it, get it shipped and check it out, and here it is, right here. But this is not the Pac-Man power supply. eBay! Now, it's not eBay's fault. It's my fault, because I don't know if you do this, but whenever I'm browsing eBay, I always read what I want to read and not necessarily what's in the text. This is a power supply for a Super Pac-Man, which came out much later. This may also work for Bosconian and a couple of others. I gotta check it out. So, but it's not gonna do what I want for the Pac-Man. It's not a total waste, because maybe I'll build one of the other arcade units that it's for. But it does have a couple of transformers, but not the transformers I need. So, lesson learned. Got to be very careful when you order things on eBay. So, let's talk about the Pac-Man and the Miss Pac-Man and what it needs to power it. So watch this.
Okay, this is a presentation about how to power Pac-Man, which of course is the same for Miss Pac-Man and Galaxian. This is going to start from how we get the power from the wall and turn it into something that the arcade machine uses. So if you were to measure the voltage from your wall, you would see it was alternating current from 120 volts to negative 120 volts over 60 hertz. That's 1/60th of a second. That's the standard power in North America. And this is what we have to start with. Now, this isn't what we need for Pac-Man. Pac-Man needs two other voltages. It needs plus 12 and minus 12, and plus 7, minus 7. So what we do is we take the power from the outlet and we wind it up in a spool and put that spool around a core. A core is a special magnetic material that has a lot of free electrons. And what happens is the winding around this core with the 120 volts will cause a magnetic field which will force the electrons in the core to rotate around them. and it goes back and forth based on the frequency of the alternating current, which of course is 1/60th of a second. That's the standard. So once the power is energized, the electrons will travel around the core, and there's no connection from the windings to the core, no electrical connection. It's all through magnetism. So we have this energy now going through the core in the form of electrons. So to get the voltages we want, we do other windings on the other side. This is called the secondaries. And depending on the number of windings we have around it, we can pull a different voltage out of those electrons floating around the core. So if we have 10,000 windings at 120 volts, we can get 24 volts out by using 2,000 windings. And we can get 14 volts out by doing 1,167 windings. So this is the 24 volts across both of those endings. Now what we want is, we want a plus 12 and a minus 12, so we tap into the center of that winding. That's what the CT stands for, it's center tap. And what that does is it gives us a ground or a common voltage right in the middle. So half of 24 is 12. So we can get a phase 1 or plus 12 volts AC and a phase B, which is minus 12 volts AC from that one set of windings. And the other set of windings, we can get a plus 7 and a negative 7, which is exactly what the Pacman motherboard wants. Now, that's what the power system of the Pacman motherboard. The circuitry wants a digital current. Pretty much all electronics wants direct current. So once we get these AC voltages to where we want them, we need to turn them into DC. So how do we do that? Well, we take this alternating current that's going through these cycles at whatever voltage we have, and we run it through a rectifier. So a rectifier is a series of diodes. Diode is a circuit that allows the electrons to pass in a certain direction and blocks it the other direction. So when it's in one phase, you can see the power will go through the top set to the top of the VDC, and that will give us the wave, the alternating current wave through the top portion. Now when the current or the voltage goes below the center line there, it goes through the other set of rectifiers, but see, it ends up on the top again, just like the other wave. So now you can see that chart has two bumps on the top instead of one above and one below like before. So that's what rectifying does. It makes everything a positive value. But you can see that there's really bumpy. This is not very direct current. It's not very clean. So we have this smoothing circuit over here. That's this big capacitor and resistor. What that does is the capacitor acts like a bucket. It fills up with charge, and the resistance keeps the voltage up and allows it to slowly decay. So you can see if we take a couple of these cycles and we smooth it, you can see we can have a voltage line that's fairly high, slowly creeps down, and then it fills up again when it hits the bump from the alternating current. So this gives us sort of a direct current, but as you can see, it's kind of bumpy. It's not very smooth or not very clean. So we need to do one more treatment to it to make it a nice, clean, solid direct current. And that is with a diode, but a special kind of diode we call a Zener diode. And what this does is it blocks the power. It doesn't allow the power to go through, just like diodes, but then it has a breakdown voltage. So after a certain voltage, it'll allow power to flow through, which means when the voltage is too high, the Zener diode will allow that extra voltage to pass out to ground, so it makes it nice and even. So see here we have the 5 volts, but if we have 6 volts comes through, when it hits the Zener diode allows one of those volts to go out to ground and keeps everything at 5 volts. So as you can see our diagram here, instead of a bumpy, choppy, hilly wave, we have a nice single solid clean 5 volts going across here. So what happens is we start with 7 volts because we're expecting this bump to go up and down, but finally the Zener diode will clean it up to 5 volts, which is what the electronic circuits inside Pacman want. And we do the same thing with the 12 volts. We clean it up and we drop it down to 10 volts, which is used for the amplifiers and for the video voltages. So this is how we feed the Pacman nice clean energy. And clean energy means a happy Pacman.
I went searching around for the exact power transformer that I needed. Couldn't find it, so I contacted some custom transformer companies, and I got the results back. And I'm going to switch to the 3D view and show you what I got for the results. I had contacted about five or six companies, and I said, I need this transformer. This is from a Pacman, and they don't make them anymore, and I need something that provides this power. So I gave pretty much the same information to all of them, and let's see. Let me just write down. I'm not gonna put out names there. I'm just gonna write down what the results were. Okay, so there were 5 companies, and the first company took about I'd say 3 weeks to get back to me, and I also told them that I'd probably be interested in getting about 20 of these throughout the year, just so that it's not a single thing. These companies, they're in it to make money, and so you can't just go in and say, hey, I just need one. I'm a tinkerer and I'm just screwing around. I just want one. Please spend time and resources to make me the one. They came back and said it'd be $280 per unit. That's each. If I buy 20. The second company came back just recently, and they said it was I think 70. Oh, yeah. Let's say $80 each if I buy 20. They did, however, also come back and say, well, if I buy 100, I can get that reduced to $60 each. So that's kind of not too bad. I can get it with 2 separate transformers, right? 2 transformers for a total of $30. So, the convenience factor of having it in a single transformer with all the power, double that. That's not too unreasonable. But am I going to be able to sell 100 of these? I don't know. That's quite an investment. Am I going to have to invest $6,000 and possibly get stuck with a whole bunch of old transformers? I don't know. Don't know if I want to do that. The third company said, why? Why are you doing this? Why don't you just get 2 transformers? All right, and be done with it. And that's a really good point. I can get 2 transformers for $30. The fourth company said, no, they don't work on anything that small. The fifth company came back and said, oh, yeah, we can do that for about $80 each for a quantity of 20. They didn't give me any pricing information for a larger quantity than that, but that's, this seems kind of reasonable. They seem very, very exact. This price right here, I think this is a price called no. We don't want to say no, but we're going to price it so much that you're not going to want to do it. So I think number 4 and number 1 are pretty much the same. Not going to happen. This is a possibility. This is a possibility. And this, of course, actually, let's just put X's there. That's just not going to happen. So, do I want to invest, right, if this is 20, do I want to invest $1,600 to get 1 transformer and sell 19 others? Am I going to be able to sell them for 80 when other people can go get them for 30? Yeah, that's kind of a risk. So this is really looking like the option to get 2 separate transformers. I'm also kind of stubborn enough that maybe I'll do an episode and I'll wind my own transformer just for the heck of it, because I'm pretty silly. Now, these companies are all over the U.S., and there happened to be one company that was pretty close to my house up here in Sacramento. It's a company that's in Stockton, and I called them up and said, hey, can I get a tour of the place? And they said, sure, come on down. And so I met and talked to the engineer who was working on my project, and I got a little video to show you about that. And so let's take a look at that right now. And when we come back, we'll talk about what we're going to do. Hi, thanks for joining us. I'm here with Jacob at West Coast Magnetics, and we're here to talk about custom transformers. And I submitted the custom design, and Jacob took it up and called me back and forth to make sure all the numbers were looking good. And I'm here to find out, Jacob, what happens when you get a design, and how does it actually become a completed product?
Yeah, so we get the RFQs from usually the sales account, and Brian contacted us through the sales account, and then if we bid or no bid the project, we can reach out further to the customer. So that's what we did, and we took all Brian's design requirements, and based on a previous standard product of ours, came up with a transformer design for 60 hertz, just simple primary 120 volt input with 2 center tapped secondaries on the output, and through a little bit of back and forth, came up with this design.
All right. So once you know that, then you know what kind of core you need and how much wire and what size wire and that sort of thing.
That's correct. Our standard products previously had like set bombs where we have the bombs for the geometry. However, the wiring and the configurations are all specific to the customer. So we have standard bombs that we pull from that are easy to quote, and then we just fill in the blanks on the wire, basically.
All right. So was this design pretty similar to some of the other custom designs?
Yeah, pretty similar. This is one of the smaller lamination transformers that we've done. In the past, we've done other ones that are this big, and even some EI lamination transformers that are about this tall.
Whoa.
And weigh like 40 pounds, so they can get pretty big and pretty heavy too.
Yeah. So are you typically doing mid-size, large, or small?
Typically, this is the smallest size out of our standard products. I would say no bigger usually than 6 inches by 6 inches.
Mm-hmm.
That way we just save on shipping costs, save the customer shipping costs, but also we never ship anything out on a pallet here. So we have to be careful with how big these things can
Right.
They have to fit in a cardboard box.
Right.
Yeah.
So once you know how much material it is and how big it's going to be, do you have to, are these like handcrafted, or are they put into a machine, or
These are hand wound, and you'll see other parts, not laminations, but other parts. They're all hand wound. We pretty much have a few tools in-house available for automated winding, and you'll see one of those tools on the tour. But the other ones, they wind just toroids with wires evenly spaced, so that doesn't, and that still requires a lot of operator input. We don't have a machine where you press a button and it does
It's just not magic.
Or a machine that you dump a bucket of 1,000 toroids into some input and boom, you get these beautiful inductors output. So it's all like, call it bespoke, transformer
right
design.
So it is still like a handcrafted kind of a manufacturing process.
Yeah, no, it definitely handcrafted.
Right.
And a lot of designs are on paper too. No, we like to do that before we do simulations, because simulations get expensive.
Right.
We don't want to bill customers for that simulation resource and time. So we do our best on paper, and then we utilize the experience that our operators have to perfect the designs on the floor.
So when it's something like this design where it's very familiar and there's several things that you've already done that are similar to that, you don't really need to simulate to the full extent.
We don't. We have certain design parameters that kind of always stay true. So like flux density is a good example for the line transformers, I guess you could say, where we can always have similar constants depending on the design and what the duty cycle is and how long the part will be on versus how long the part will be off to make sure we're not driving it too hard.
Right.
So there are like key words and key variables that don't really change each design, but then it's really your voltage inputs that are the difference makers and the power rating that you expect out of the design.
Because after a certain voltage and amperage, there's a thermal to consider, right?
Right. I mean, transformers get hot regardless, but how hot is the question. These, we drive the core losses pretty conservatively for our designs. If we don't know the customer's like on or off time, but it's pretty much dependent on your input voltages, as well as some customers even have like, they pre-calculate what the DCR should be on a winding. So sometimes we'll get like DCR should be no greater than 100 milliohms. That way they calculate the losses from the copper and they can figure out if it's going to get too hot or not.
Right. So do you do just copper windings here, or do you do aluminum?
Yeah, mainly it's all copper conductors. However, copper solid strand, Litz wire, foil, you name it. We are pretty well versed in a lot of different types of conductors that are used for these kind of. The thing is that we really don't do a lot of these. We used to do more of them, but I think it's shifted to more high frequency RF filtering.
So it's more the like radio communication type stuff. Yeah.
Switching with power supplies, stuff that switches at like above 100 kilohertz to 1 megahertz.
Switching power supplies, you said?
Yeah.
Okay.
So we design like the transformers that go in them and that are used to be the main source of voltage step up or step down.
Yeah. See, the whole reason I'm doing this design is because the logic board just takes AC. There's no DC connection, so I can't just use a switching power supply. I'm kind of like stuck with this.
I see.
So it's a motherboard made in the 80s. So it's like it's the Pacman motherboard actually.
Wow.
So it's the whole thing's on one logic board, and it has its AC to DC connections to it, and drives everything else. So I could get like a switching power supply, but I would have to reroute and disconnect and do a whole bunch of hacking on the board, and I really don't want to do that because that's going to break something, I'm sure.
Yeah.
So, good. Is that a lot of wire, copper wire? Is that expensive, or has copper come down? Because it used to be outrageous, the price of copper.
It depends really on our distributor that we buy it from. Like, I know we buy a lot from MWS, or we try not to, because they're typically really expensive. We haven't really gone to like Chinese suppliers, to my knowledge, on wire. Typically, all our wire is U.S. manufactured.
All right.
all of our copper
Go
is
US.
manufactured. And there's also just, if you get to know people in this industry, you realize there's not a lot of companies that do it out there in the US. Even laminations, there's like 3 companies in Chicago
Right.
that make them. Because
Is it just because of the labor costs?
I think so, but also people are coming up with more interesting ways to design like transformers, and also the size that we use is not really the most popular anymore. I mean, like, people either use laminations for like really small stuff like this, or like huge line transformers, 3-phase.
Right.
We just got a quote request actually from a 3-phase customer, and
Wow.
we don't do any of that, so
Right.
we kind of have to no bid those projects.
But you're kind of filling a niche that's just sort
We
of being overlooked.
Yeah, definitely the custom niche is what we fill.
Yeah,
I
yeah.
think you could go to any large
Like
manufacturer
Hammond
and
or
get like standard, 100.
Are you confused? So am I. I'm not sure what happened, but the video just stopped working at this point. So I'm going to skip ahead to the other little bit of video I have, which was towards the end of the tour, which I couldn't show much anyway because of NDA.
Look at all that beautiful copper. Very cool.
So those were the results from the custom companies. I'm not sure if there's going to be enough of a demand for me to sink that much money into getting these transformers. And of course, the other cheap route was to, instead of getting a single transformer to provide the power, just get off-the-shelf transformers for doing the individual powers. Here are some individual transformers. So they only have a single secondary, unlike the one that came with Pacman. And so this one is the 14 volt. So it gives me 7 VCT. And this is the 24 volt. So this gives me the 12 VCT. This one cost $15. This one cost $15. So it's a total of $30, which is a lot cheaper than, the $76 if I buy 20 of them. So this is definitely the cheapest way to go. And newer transformers, it's a lot smaller than the transformers that were in those units. So, but it provides enough power. I also have here the fuses to protect the circuits and the systems from going over voltage. So I have pretty much what I need to build the transformer block for the Pacman. What I don't have here is the isolation transformer, which is needed for the CRT. But that's kind of a separate issue. I don't think I'm going to be able to get a CRT. I think I'm going to have to get an LCD, which means I'm not going to need that isolation transformer. I'm waiting for some fuse blocks and some bus bars for protecting the connections so that they don't get loose, and then I can screw it into a board and we'll have the power section done. All right. And then after that, we're going to start working on the other electronics we need, which will be the control panel and the speaker and the coin door. And then finally, we'll get to the display situation. All right. Well, I hope you liked this episode, and subscribe if you like, and be notified when we get the next update. Okay. See you later.
All right, there it's going. I was waiting for the one signal, that's all.
Okay. There we go. Hi, everybody. I'm here at West Coast Magnetics, and I'm talking to Jacob, who's been helping me with the transformer design. And I'm here to find out how it goes from a design to an actual product. And
She needs me.
she needs you. Okay. And we wait.